Hey, welcome back to Math with Patrick and Quill. Today is December 30th, and we're solving problem 364 from the Daily Epsilon calendar. The answer today should be 30 because that's today's date. So we have a fraction. This should be the number 30. In the numerator, we have the sum of three different choose functions, and then in the denominator, we have another choose function. I think let's talk a little bit about what this means before we tackle the numerators. Here, this reads as 5 choose 3. This counts the number of ways we can choose 3 objects from a total of 5. What's kind of interesting about this is that 5 choose 3 and 5 choose 2 are actually the same number. Because if you think about it, choosing 3 objects is the same thing as not choosing 2. Or rather, choosing 2 to then throw out. So either way, 5 choose 3 and 5 choose 2 should be the same. And I just want to walk through all the different options of choosing 2 things from 5 objects. This way we can be really, really sure what this number is, and then we can generalize it with the formula and use that formula for the top ones, because these numbers are going to be a bit bigger. Here, let's count methodically. Let's start with definitely having this first object in our pair, and then count how many pairs we have. 1, 2, 3, 4. No big deal. Now we know that we've counted every single possibility of choosing this one and another one. So as we walk through other possibilities, I don't need to think about going back and choosing that one again, because I've already accounted for that possibility. So starting with the second object, I have 1, 2, 3. And then we can continue this process until we've counted all the pairs. 1, 2, and then 1. So 4 plus 3 plus 2 plus 1 gives us 10, and that's the exact value of 5 choose 2, and that's also the same value of 5 choose 3. Another way to think about this is if we have a collection of 5 objects, we can think about how many options we have as we take objects from that pile. So thinking about this 5 choose 2 example, we have 5 different choices for our first object. And then once we've chosen that one, now we have 4 objects to choose from. And so we do have 5 times 4 or 20 options when choosing this way. Though this does suggest that order matters, because I am counting, say for example, object A, then object B, differently from if I chose object B, then object A. Currently, in my counting scheme, these are different options. But when we're choosing from a group and we don't care about the order, I don't want these to be distinct. So to compensate, I will just divide by 2, because every single pair, let's say AB, is going to have another pairing, in this case BA, that I'm currently double counting as different. And this divide by 2 makes sure that I count these both as the same. We could also run through it with the idea of 5 choose 3 instead. So we still have 5 options for the first object, 4 options for the second, and then 3 options for the third object. And then here, once I have my 3 objects, there are actually going to be 6, or 3 factorial, different ways that I could have chosen them in different orders, but then again, order doesn't matter. So this 3 factorial considers the fact that, say, ABC, ACB, BAC, BCA, and then finally CAB and CBA, all of these orders of choices are all going to be the same thing. And so I'm dividing by 6 here to make sure that I'm counting all of these as identical scenarios. 3 factorial is 6, right? It's 3 times 2 times 1. And then to simplify this multiplication, I could cross off these 3's, maybe simplify those 2's, and then I can show that this number is also 10. And this kind of counting scheme and then crossing out our redundant pairings or redundant groupings is where a formula for our choose function can come from. In the numerator, you can see that we have this descending product starting with 5. 5 was the number of items we have. And so in a more general sense, if we had, say, n items and we're choosing k of them, we would start with an n factorial in our numerator. Now, this times 2 times 1 is noticeably gone from the numerator, just like how this times 3 times 2 times 1 is also gone from that numerator. So we could cancel it out with the same factors in the denominator. right? So this 2 times 1 could have been canceled by another 2 times 1, or up here, the 3 times 2 times 1 could be canceled easily with another 3 times 2 times 1. And so here I introduced some kind of factorial on the top and bottom. And let's say this was our example for 5 choose 3. The way that I'm getting this number 2 is by finding the difference between 5 and 3. So this factorial right here, the one that's helping me cancel some factors already in n factorial, is going to be n minus k factorial. We first find the difference of these two numbers, then take the factorial on the bottom that helps us cancel those extra factors in the top. Now we can see that this remaining product we could write as, well, in this case it was 3 factorial. That is just the bottom number right here. So in my general formula, I could call that k factorial. And this right here is this factorial formula that we can use to more quickly evaluate the numerator, or the addends in our numerator. Maybe let's start with the smaller numbers first. Using the formula, 6 choose 3 is going to be the same thing as 6 factorial over 3 factorial times, and then the difference of these, which is 3 again, factorial. One way to double check that you are doing this formula right is if both of these numbers add to 6, or in a more general case, both of these numbers need to sum to n in the top. And writing this all out, we have 6 times 5 times 4 times 3 times 2 times 1 in the top. And then I am going to just automatically cancel out that 3 times 2 times 1 with, say, this factorial on the left. And then now we just need to figure out what 6 times 5 times 4 divided by 3 times 2 times 1 is. Fortunately, 6 and 3 factorial are the same, so we are just left with the number 20. So all we have to do is do this 2 more times, and then we'll do divide by 10, and we'll get 30. So hopefully overall this number in the numerator is 300. So for the next one, we'll have 8 factorial on top and 4 factorial squared, I guess, in the bottom. We're going to get 8 times 7 times 6 times 5. I'm not writing the other ones because I'm just kind of canceling them with that 4 factorial in my head. And then 4 times 3 times 2 times 1 in the bottom. So 4 times 2 creates an 8, and then I can simplify that 3 with the 6, and I'm left with a 2. So I have 10 times 7, which is 70 left over in the top. So now that that number is 90, I'm hoping that we get a 210 out of the last factorial. So we can follow the formula again, put the 10 factorial in the top, put a 4 and a 6 down here. And then I'm going to choose to cancel out that 6 factorial in my head first, just so I have fewer factors in the top. 10 times 9 times 8 times 7. Again, that 6 and onward is kind of scooped up and canceled with this 6 factorial. 4 times 3 times 2 times 1 remains. Here is the number 8 again. I can cancel this 3 with one of the 3's in this 9. And then we do get 21 times 10, which is 210. So wonderful. We do get the 300 in the numerator. Divided by the 10, we do get 30 for today. And that's our answer. So we're basically all done. There is one more thing that I thought about before I started the video, and that is that choose functions actually have a lot to do with Pascal's triangle. I've gone over this in other videos before, and I forget exactly where they are, but this is a well-known fact that choose functions and Pascal's triangle they're essentially the same thing. All of these numbers that I'm writing here in Pascal's triangle, you can generate by writing choose functions. These tens right here are actually both 5 choose 2 and 5 choose 3, the numbers that we found earlier in the video. Now, I don't think there's anything here that's interesting though, because all of these numbers are different. We would need to find the 6th, 8th, and then 10th row of Pascal's triangle to even use it to relate the choose functions to the triangle itself. So I don't think there's anything valuable to find here, but maybe I'm wrong. And maybe if you found a really nice, satisfying connection with Pascal's triangle, apart from just grabbing the number itself, let me know. So this is my solution for today, and we're all done. So thank you for watching, and I'll see you tomorrow. Bye.